Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro Chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax. And on with the show.
More like once it gets in the fence, but
I just thought it might be.
It is interesting.
Your knowledge might extend to that area.
You're on the other end of it.
Mm-hmm. Once it gets there.
Well, again, good evening. Today's presentation is on the
PFAS.
PFAS. On the table. And our speaker is Graham Sizemore. He is a PE, registered PE. South Carolina?
South Carolina.
Georgia yet?
It's pending. I just got all the NCES stuff squared away. So
good.
Yeah, getting it sent in.
And he's also a past president, state president, right? So, take it away.
All right. Yeah. Thanks for having me, y'all. So today we're going to talk about PFAS, or as you guys might know them, toxic forever chemicals. So if you see an article about that in the paper or online somewhere, generally this is what they're talking about, and it's really a pretty hot topic in water right now. I would say the hottest topic in water treatment. So today I wanted to talk a little bit about the water cycle and where we are in the water cycle and kind of today's treatment or a conventional treatment overview. I wanted to get into what PFAS are, and spoiler alert, it's more than just one thing. It's not one thing. The regulatory involvement and how that landscape is changing, treatment technologies that are currently in use for treatment of PFAS, selecting treatment, the regulatory action plan as we understand it right now, and then kind of tie it all back together. What does that mean for us? What does that mean for the future? So here you can see an overview of the water cycle. So over on y'all's left, you see source water. That could be groundwater, it could be lakes, rivers, streams, anywhere that you can put an intake or a well and draw water from the environment. And because it's in the environment, it's going to have a wide range of properties, and you got to measure those and determine what's in the water and what you got to take out to meet EPA drinking water quality standards, and here in Georgia, EPD drinking water quality standards. So as you can see, two major uses of drinking water in the U.S. are, drinking water facilities and then also industrial facilities. I don't have agricultural on there because typically they're using that to water plants, so it doesn't go through the same treatment process that we typically take industrial or drinking water through. But as you can see, it goes to a drinking water plant, goes out to distribution, gets to your homes, it gets back into the collection system, and eventually conveyed all the way back to typically a centralized wastewater treatment facility if you don't have a septic tank, and then gets discharged back into the environment where it again becomes source water. So I got news for you. The water you're drinking isn't new. It's been recycled many times. So this is just an overview of a wastewater treatment facility. And what you can see on the far left, number one, is kind of the end of the collection system, which is typically where I kind of start. So usually it's pumped up and screened, and it's called the headworks. So you screen it, you put it through a process where you slow it down to between 1 and 2 feet per second to try to settle out any grit, which is sand, fingernail clippings, things like that aren't going to be biodegradable in the wastewater. After that, you pass it into a biological treatment process. Almost every wastewater treatment plant in the United States is a biological system where you're adding oxygen to oxidize things like proteins, carbohydrates, things like that are left over in the wastewater and also soaps and things like that. All surfactants are biodegradable now, and your laundry detergent and all that. So the bugs can eat them, and they turn them into water and carbon dioxide, which is pretty cool. They call it biochemical oxygen demand, and that's one of the main things that's coming into your wastewater plant that you want to remove, along with ammonia, things like that. After that, typically it goes to a settling process, and the settling process removes the bacteria that you've grown. Your biosolids sink to the bottom, which it's not poop at that point, it's bacteria that have metabolized what's coming into the plant. And then it leaves as what people call sludge. Typically they dewater it and put it into a landfill, or you can land apply biosolids for all kinds of different stuff. But if you're doing Class B, you know, you could feed livestock with it, stuff like that. There's restrictions. And anyway, that's an important thing because we'll talk about that a little bit later. That's one way PFAS leaves a wastewater treatment plant. But after it's clarified, it goes to some sort of disinfection process. What you see there is a chlorine contact chamber, and before it's put back into the environment, it's dechlorinated. So here's a wastewater plant that I know and love, Augusta Utilities Department, the J.B. Meserly Water Pollution Control Plant, WPCP, and that's in Augusta, Georgia. And it's big. It's rated at 46.1 MGD of capacity, so 1 million gallons per day. But this is what one actually looks like. And now here's the water treatment plant. So you've got your source water all the way on the left. In this case, it's some sort of reservoir. Typically after that, you'll inject chemicals into the water. And that typically is a coagulant, a polymer, and then some sort of flocculant aid. You mix those up really quickly, and then you flocculate it. So you slow the water down. You're trying to create a G value that is conducive to making those particles touch each other and stick together with the chemicals that you added. After that, it goes through a sedimentation process, similar to what is done at a wastewater treatment plant, but in this case, it's mostly TOC, or total organic carbon, that's coming in your influent water. And that is also taken out and dewatered, usually sent to a landfill. After that, it goes through a disinfection process, or they add chlorine typically, and then it's usually filtered with sand, anthracite coal, and gravel. And after it goes through that, they'll put it into a big tank, a clear well that you can see kind of over here. They hit it with more chlorine, let it sit there for a while. They'll dose it back up with chlorine and send it out to the distribution system for it to get to your taps. So all that to say, I just wanted to kind of set the stage. This is what a traditional treatment plant is like, and what's important is none of those are designed to remove PFAS. So you don't get great removal through either the wastewater treatment process or the water treatment process. And here's a water treatment plant, the Anderson Regional Joint Water System, pretty close to us actually, only a few hours away from here. But this is what a water treatment plant looks like. So I wanted to talk about this because it was very interesting to me when I first heard about it. These compounds are being proposed to be regulated on the parts per trillion level, 4 parts per trillion actually. And so it's hard to imagine what that is, but 1 droplet of water is about 0.05 milliliters. It is 4 droplets of water in not 1, but 20 Olympic-sized swimming pools. So 4 droplets of water in 20 Olympic-sized swimming pools. And it's really hard to measure when you get down to these concentrations. So there's actually, you know, not a ton of labs in the country that can measure it accurately down that low. And it's pretty expensive to, you know, test for these compounds. So to put that in perspective, that's over 55,000 tons of water. A lot of water with just a little bit of chemical in it. So what are PFAS? So they are comprised of fluorinated carbon chains that are attached to functional groups. And they include carboxylic acids, sulfonic acids, alcohols, and other different compounds. They're typically composed of an alkyl chain that's 2 to 16 carbon atoms long, and you can see the molecular structure there. And what varies is this chain, and it can affect how easy it is to remove through different technologies. And what's important about them, or what initially was important about them and why they became so widespread, is that they're extremely strong and stable. They're both hydrophilic and lipophilic, so they repel water, they also repel fat, and they're very difficult to break down, very stable. They're going to stick around for a long time. So because of that, it made it very, I guess, attractive to industry. And we'll talk about what it's used in a little bit later. But they're man-made compounds and used since the 1940s. They stand for per and polyfluoroalkyl substances. And you can see kind of the breakdown here. There's PFAS, there's per and polyfluoroalkyl substances. And within polyfluoroalkyl substances, there's PFOS and PFOA. And then below that, you know, PFHXS. So there's a ton of them. There's over 5,000, and it's almost impossible to pronounce half of them. You really have to practice to just get one of them. But
just those top two is a good accomplishment at pronouncing them.
well, thank you. I had to practice for a little while, so it didn't come overnight. But again, it's a broad spectrum of different compounds that are manufactured to resist stains in clothing. They also make nonstick cookware, so Teflon is a PFAS compound. And they're found in aqueous firefighting foams, metal plating, textiles, photography, electronics, paper coatings, paint, hydraulic fluids, and many more. So they're really all over the place. So this is just a diagram that shows kind of how PFAS gets into the environment and comes back out and is introduced to us and allowed into our bodies. So there's PFAS producing or using industries. And again, even if they're passing it through a wastewater treatment facility, or if they have a wastewater treatment facility of their own, they weren't traditionally regulated. So, and the typical traditional methods of treating wastewater don't remove them very well. So they're making their ways into our water bodies, and you'll see just in a little bit how widespread they are. They're detected in just about everything, which is pretty nuts. And again, you see the wastewater treatment plant there, discharging biosolids, which we talked about earlier, which can contain PFAS and PFOA. Firefighting foam that, you know, is just drained directly through storm drains and things like that that don't have a formal treatment process. It can actually end up in food as well and make its way to your plate, and also your drinking water. So reasons for concern, there are known or suspected health concerns regarding PFAS. They are widely used in a variety of industries across the world, highly persistent, they're mobile in groundwater, and they also bioaccumulate. So 97% of Americans have PFAS in their blood, at least the ones they've tested. And 19 million Americans are served by drinking water systems that are affected by PFAS that we know of. So here are some of the recent, yes, Luther.
What are the
Basic measurements for those figures you just gave us, the 97%. I haven't been tested that I know of.
So out of the studies that they've done, and I'm not actually, I haven't read into the study. I just know that that's the number that they quote typically. So
I did read on this, since I did some writing for the news release. It struck me the EPA study was a relatively small sample
well, yep.
out of the whole country. They did not test private water supplies. These were only public water supplies that they were looking at.
So I'll say this, while the sample size may be small today, relatively small, it will definitely be ramping up in the future, no matter what anybody has to say about it, because it's a big topic of concern, and people are testing for it, and it's going to be, if not a requirement, more and more widely tested for. So anyway, some of the health effects that people have come out about recently are hepatic, and I'm not the medical guy at all. So cardiovascular, endocrine system, which is it affects your thyroid, immune system issues. It could cause reproductive issues, developmental issues like decreased birth rate, and then also there have been signs of an increased risk of cancer. So for those reasons, that's why the concern is around, according to those studies, this happens in very low concentrations, can still be harmful.
Graham, I guess my real concern is
They have overdone this climate problem, and I'm concerned that they'll overdo this. It's just another panic thing for us to panic over. Has there been anything in the way of okay, what permission do they have to test whose blood to see that they have this?
So I don't know. I mean, I really don't
Okay.
know a lot about how they're going about testing blood or what they're doing to, actually do these studies. Again, this is something that's being handled from a regulatory standpoint. Really kind of my focus is what are they and how do we remove them? And if it's going to be a requirement of the US EPA and thus, EPD or SCDHEC, then we're going to have to remove them. And so great questions for those entities. I'd be curious to know their answers myself, but if they're going to be regulated, we got to remove them somehow. So anyway, this is a map, and it shows areas that PFAS have been detected. Some of them are on military sites that are in purple. Some of them are in drinking water, and you'll get to see in a second how they are currently measuring PFAS in drinking water, and then just other known sites. And what's important to note is that the states with more sites are just the ones that have done more testing right now, because odds are, I mean, you're testing down to these really small concentrations, you're probably going to find it, if you go looking for it. So,
Well, that explains why it breaks off the border of North Carolina.
and so, this map, I mean, it's changing every day. It's probably different now already, but just kind of shows how widespread these chemicals are. This is a timeline about regulatory involvement. So in 2000, industries began voluntarily phasing out PFAS use. In 2012, the EPA began monitoring PFOA and PFAS. And then there's something called the Unregulated Contaminant Monitoring Rule. And every time they do another one or add chemicals or change the requirements, they add a number to it. So it first came out, and it's called UCMR 3, which basically means, hey, you guys aren't regulated on it yet, water treatment plants, but you have to test for this chemical. We want to see, how widespread the issue is or what concentrations are actually out there going into people's drinking water supplies. And so Method 537 was developed by the EPA to aid in measuring 14 PFAS compounds, and it required sampling from public water supplies, PWSs, serving more than 10,000 people. And then in 2016, the EPA introduced a drinking health advisory limit of 70 parts per trillion, so 70 drops of water in those 20 Olympic swimming pools, for the sum of PFOA and PFAS. In February of 2019, the EPA published a PFAS action plan, which we'll talk about a little bit later in the presentation. In 2020, preliminary determination to regulate PFOA and PFAS, interim guidance for destroying PFAS-containing material, and also they validated a method 533 for measuring short chain. We talked about how long those chains are, PFAS that year. In 2021, there was a toxicity assessment for PFBS, another PFAS compound. And again, we can probably glaze over a few of these, but what's important is earlier this year, March 14th, they came out with a hazard index and also proposed maximum contaminant level, or MCL, for PFOA and PFAS of 4 parts per trillion, and then the hazard index for those other compounds of 1. And so, 4 parts per trillion, that's 4 drops, 4 nanograms per liter. So these are the substances that are receiving regulatory involvement right now. And as you can see, it's just a small part of a much longer list. And like we said earlier, this list is certainly not comprehensive. There is over 5,000 chemicals that have been identified. So how do you treat it? How do you remove it from water, especially in these low concentrations? There are 3 treatment technologies that are currently available and widely used that are successful at removing PFAS from drinking water. Those are PAC and GAC absorption, which stands for powdered activated carbon and granular activated carbon, ion exchange resins, and also nanofiltration and reverse osmosis, or high pressure membranes, the same technology that they use to desalinate. So this is a little bit about PAC and GAC absorption. GAC is the most widely used, so typically it's a deep bed filter with granular activated carbon that you would pass water through, and this is in addition to those treatment processes that we talked about earlier. And longer chains are more readily absorbed by this method. The shorter chains do have a little tougher time being absorbed, and lead lag systems are fairly common, and they require 7 to 15 minutes of empty bed contact time, or how long it takes the water to percolate through a clean mass of granular activated carbon. And typical carbon sources for this are bituminous coal, virgin or reactivated, so you can pass high current through it. I don't really understand the electrical part of it, but it's some sort of electrical process where you can regenerate it. And then also coconut. So ion exchange, PFAS are attracted to ion exchangers. It's a positively charged anion exchange resin, or AER, and it attracts the negatively charged PFAS. There's no waste stream to handle because they're incinerated after use, instead of, GAC, typically you have to take that to a landfill or reactivate it. And then it requires a much shorter empty bed contact time, 2 to 3 minutes in a lead lag scenario to handle swings in flow and demand. And then finally, nanofiltration and reverse osmosis. So this one is really expensive because you have to provide super high pressure, so it just uses a ton of energy. You have to super pressurize the water. You get really high transmembrane pressure to drive that reverse osmosis. Again, this is how they remove salt from seawater typically. And there's a little bit of a problem with it because it does create a really highly concentrated brine, and this happens with salt water, but it also happens with PFAS. It's just concentrating that stream down, and then you've got to deal with it some way. So again, not shown to be effective. Pretty much everything we talked about earlier: aeration or air stripping, biological filtration, biological treatment, low pressure membranes, which are nano and microfiltration, which are more commonly seen at water treatment plants if you have membrane filtration, compared to high pressure, which is nano and reverse osmosis. Chlorination, conventional treatment, like I said, ozone, UV, or other advanced oxidation processes. So really pretty resistant. There's not a lot of ways to remove this stuff. So this just compares the different methods for treatment. It also displays what you can expect to remove with these different treatment technologies. So generally, as you move down the page, it becomes more effective, but it also becomes more expensive, and there's trade-offs, like probably the most effective reverse osmosis. It's very expensive, and also you have a concentrated waste stream to deal with afterward. So selecting treatment, how do you go about deciding which one is right for your water utility? Well, there's planning considerations. preliminary treatment evaluation to see what's actually going to work, what's going to get the removal that you need, pilot scale testing, which helps confirm that. Then there are key parameters that you want to monitor as you're doing the testing. So there's other things like total organic carbon, alkalinity, pH, that can affect the outcome of how effective your treatment is. And then I'll have a little bit of a summary of PFAS testing. So planning considerations, typically start out with a questionnaire, distribute that to the folks at a water utility, sometimes members of the public, just try to get an idea for what the feeling about it is and also what kind of treatment technology they may be most interested in. There's a lot of operational considerations and then also cost considerations, so it's important to involve people throughout the process. Really to define your treatment objectives, and obviously some of that is just dictated, but sometimes, you know, there's a goal that a water utility is trying to meet that's maybe above and beyond that. Water demand, so how much water do you need to be able to deliver and how quickly does it change? Making sure that you have the right turn down so that your equipment can hit those low flows as well as the high flows. And then the concentration range in your influent water. So what's coming in, how much of the PFAS are you trying to remove? What's your water quality coming in? Because it's also really important. I mean, like I said, there's things that can affect the outcome of how effective your treatment is. And then how do you implement it? So this is some ways that you can do preliminary treatment evaluation. Bench scale testing, so this is probably the least expensive. It's what you would like to start with ideally. And this is different ways of testing powdered activated and granular activated carbon. You can see jar testing over there on the left. So mixing up powdered activated carbon and testing the removal rates of it. An isotherm test where you allow powdered activated carbon to be introduced to water with PFAS, and again, a way to measure concentration that you're able to remove. And then a rapid small scale column test. This is similar to like a granular activated carbon filter. Then pilot scale testing, so stepping up the range of expensives, more expensive. And then there's also timing and duration. You got to coordinate with manufacturers to get equipment out to the facility and also the facility itself to make sure that there's things like power or wash down water that they may need. Testing conditions, so you really want to be making sure that you're monitoring everything that's coming in, everything that's going out, so that you have a firm understanding of why your treatment may be working or may not be working. You want to make sure you get the right equipment. Again, monitor it well, have staff that are trained, know what they're doing, and able to communicate that with people, especially if it's a newer technology that they may not have used at their treatment facility. So, you know, it's important to make sure everybody understands what it's doing and why we're doing it. And then quality control, just making sure that everything's functioning as it should be. So some key parameters that you really want to take a look at, and again, I probably won't run through all of these, but pH, temperature, dissolved oxygen, conductivity of the water, which can measure how much, you know, dissolved ions you have in there, like salts and things like that. Total organic carbon, UV transmittance, UVT, oxidation reduction potential, ORP, turbidity, and the list goes on. There's a lot of things to keep in mind whenever you're testing out one of these systems, and a lot of things that you need to understand about the water that's coming into your system. And again, this all goes into creating a good library of pilot scale testing data so that you're able to crunch the numbers later on when it comes time to install something that's full scale. So this is the treatment testing summary, and again, as you go to the right of this, I think, yep, you're right, it gets more expensive, but it also is maybe a little bit more comprehensive, a little bit closer to what you would think of as the real thing. And so typically they'll start with jar testing, something like that, and then move to a full-scale pilot testing. So future timeline, again, I mentioned earlier this year, they came out with MCLs for PFOA and PFAS and a hazard index requirement for those other compounds that you see there. And right now they anticipate having January 1st, 2024, a final rule. There's been a lot of discussions. I mean, this is an expensive undertaking for the industry. So we'll see what ends up coming out, but there's a lot of discussion around exactly how this is going to all shake out at the end. So then in 2026, it's expected that if everything holds true as far as the timeline, the final rule will be implemented. So that's when it becomes enforced. So they have, about 2 years to try to get these in place and start treating the water for it. And then, 2026 is when they would start. 2027 is when they need to be installed for compliance 3 years after the final rule. So some important points to note about the draft rule. So the EPA economic analysis assumes the final rule at the end of 2023, so pretty soon here in January, and compliance by 2026. So basically 3 years to get those. If you have an issue, know that you have an issue and get something installed to be able to treat for it. Small water systems, they'll conduct ongoing monitoring at most once per quarter. So these are water systems that are less than 10,000 people served. So again, mentioned earlier, if you're above 10,000 people served, that's when you were required by the UCMR to monitor and record PFAS. And so UCMR 5 data it's been expanded, so you're now having to test for a wider range of PFAS chemicals, and it may be used to satisfy the initial monitoring requirements if you're one of those utilities that has been required to monitor these things already, if you serve over 10,000 people. So this is a little bit, yep.
As a percentage of the overall, how many of those utilities would be serving fewer than 10,000? Is it 1%, 2%, 10%? Is it the majority?
It's a good question. I mean, there are plenty out there that serve fewer than 10,000. I wouldn't know a percentage, but would definitely be happy to look that up and try to find that.
Question, these fewer than 10,000, what kind of expense are they going to face in doing the required testing?
So, I don't remember off the top of my head the cost of the testing right now. I think it's like a couple $100 per test as it stands right now. So if you're doing a decent number of testing, it adds up pretty quickly. I think that's the reason why, they're only going to be monitoring it most once per quarter. So they're trying to limit the impact it has financially on those smaller systems that may not have the resources of a larger system. Yes, sir.
I commend you for an excellent, thorough presentation. The basic question to the average American, so our tap water is going to be better than the commercial purchase of bottled water? How do we know what we're buying?
I don't know. Some people would argue in certain ways it already is, at least in some parts of the country. So it depends on what you're concerned with. I was at a conference probably 2 or 3 years ago, and it was kind of, PFAS was still a hot topic, but it was just a hot topic in kind of the water circles. People outside of it didn't really know what it was. There weren't all these articles about toxic forever chemicals yet. But this one guy had just gotten his PhD, and he had done a study on microplastics in water, which was a pretty hot topic at the time, still kind of is. But there are microplastics small enough that they can cross the stomach lining barrier and get into your bloodstream. And so he was attempting to count microplastics as a concentration in water. And out of everything he tested kind of a wide variety, but bottled water scored the worst because it's in plastic, and tap water scored the best. It had the least microplastics. So depending on what you're looking out for, it's definitely going to be. So if you're doing some sort of adsorption technology, right? It's not just removing PFAS. It's also going to remove other contaminants and purify the water further. Now the water's still perfectly safe and regulated, yeah. So it will be of, I guess you could say, a higher quality, right? It's going through an additional step. It's removing additional contaminants, particularly in this case, what we're focusing on is PFAS. But it is interesting, and most bottled waters are actually tap water, but they send it through a reverse osmosis process, which is one of the treatment technologies. Now, not to say that your drinking water is going to be reverse osmosis, because it probably won't be. Likely it'll be one of the other technologies, just because it can be prohibitively expensive. But yes, there will be, if everything holds, there will be some additional treatment going on.
Graham, has there been any studies of how you might flush it out of the blood system?
So not that I'm aware of. I'm sure there are. I'm sure you could find plenty of stuff online. Some detox plans, maybe like a green smoothie or something that you could drink. But I mean, I would imagine, so it does bioaccumulate. And I don't know a whole lot about how, those chemicals interact with your body and your tissue. I'm not sure how you would get them out, but that is an interesting question.
So what we have here is an accumulation of forever chemicals in our body against how old we can get.
That's right. That's right.
If you live to 1,000, this will kill you.
Okay.
You're probably not aware, but 50 years ago, one of the riddles was, what's the difference between mother's breast milk and Four Roses whiskey? The whiskey does not contain DDT.
Oh, really? Huh. Another bioaccumulating chemical, right? Yeah.
The question I asked
Ask you, Graham, may sound kind of silly, but back when we first encountered the effects of nuclear bombs, the radiation effects,
we were worried about what effect it might have on reproduction. And the answer came out, don't worry about it, you'll be dead before your reproduction system can get to you.
Oh, wow.
that's true.
Yeah, just a quick question. How do the U.S. standards compare with, say, Europe, Western Europe, England, Germany, France?
So I'm not up to date with the European standards, but I'm sure that, if they aren't already there, they're coming, and in a country like Europe, I'm sure that, if they get there first or we get there first, I'm sure whoever is second is going to be soon to follow. But anyway, it's interesting. Right now, it's just being regulated at the drinking water level, but there is a lot of concern, or I guess anticipation, that it will be regulated on the wastewater side too, because, ultimately, how does it get into the drinking water in the first place? It's discharges and stuff, right? So there's been even some speculation about, okay, well, maybe we invest in upgrading the water treatment plants to remove the PFAS that's in the environment that is coming in with our water, and then further down the road they regulate it at a wastewater treatment facility, and it starts to clean up the water, right, that's actually out there. So maybe you don't need as much treatment on the water side, but who knows? This is kind of a crystal ball prediction, but something that people are talking about right now. So anyway, again, some important points about the draft rule and something that's important to remember is for right now, it's only drinking water, but there is speculation that it could come around to wastewater as well. So the action plan that the EPA proposed for drinking water is under the Safe Drinking Water Act, and it's to develop an MCL for PFOA and PFAS, which they've done, at least a proposed one. MCL. Maximum contaminant level that's allowed in the water. So it's usually, expressed as a concentration, in this case, 4 parts per trillion, or nanograms per liter. So then cleanup, again, I mentioned like moving to cleanup of streams and listing PFOA and PFAS as a hazardous substance, and developing interim groundwater cleanup recommendations. Monitoring, so proposing PFAS monitoring under the next UCMR, or unregulated contaminant monitoring rule cycle. Determining the addition of PFAS chemicals to the toxic release inventory. Surface water protection, the Clean Water Act, determining sources that require regulation, potentially regulating it in biosolids that are removed from wastewater treatment facilities, doing additional research to try to find new analytical methods to measure it, this really, really low concentration, exposure models for health reasons, and trying to determine, issues that it has in humans and animals, treatment methods for removal, and also enforcement through the Safe Drinking Water Act, and risk communication, basically to the public is the plan right now. And so the conclusion of all this, it is widespread in surface and groundwater. I mean, it's pretty much everywhere, especially in these low concentrations. Significant amount of research is being conducted right now and has been conducted in recent years. And then there are potentially significant health concerns at very low concentrations, which is why they're proposing such low required MCLs. And then it's also required to be removed through a physical process like absorption through carbon or some sort of membrane system or ion exchange resin. So with that, that's all I had. If y'all have any questions, of course, happy to answer those.
Could I get the mic? I'll make sure I use it.
There was a question earlier about what percentage of the U.S. population is served by those small municipalities. I was looking up the EPA information here, and it says 1 in 4 people is served by a distributed water treatment system, which I think is their equivalent of 10,000 people or less, small municipalities. So it could be 25% of the population is not going to be covered by those standards. For me, I mean, in this room, for those of you that don't know me, I've got an autistic child. And to this day, I cannot find anybody who can tell me why my child is autistic.
There's scientific research that suggests maybe there's a genetic predisposition to certain pollutants, certain toxins in the water, or I know vaccines have gotten a bad rap. Probably not that, but these are bioaccumulating chemicals. Do we have some concern about bioaccumulating chemicals coming up with new diseases or triggering outbreaks of things like autism that we just haven't detected yet? By the time you damage a child, it's too late. Mm-hmm. And I guess that's really the big concern here is we don't know what the health effects are going to be long term. What is the forecast? I mean, what are people saying is going to be the long-term outcome if we don't do it?
So I think that right now the health concerns that folks are really aware of, acutely aware of, are all the ones that were listed earlier. So everything from I think it's like high blood pressure, liver problems, I think also kidney, and then an increased risk of cancer. I have not been made aware of or found anything regarding potential links to autism or anything of that nature, but it is an interesting question. I mean, anytime a chemical is found to affect people in a harmful way, it's important to understand why and how that functions. And so I'm sure that over the next few years, we'll hear a lot more about what those actual health effects are. And again, they've already done a bunch of studies on it, but there will certainly be more.
Very good. Well, we appreciate you taking time, coming out here and sharing that.
Yeah, absolutely. Thank you.
I've already got one of these.
That's right, I do, but I can always use another one. Yeah, thank you. I don't think I have this one.
Oh, you don't?
The math counts one, yeah.
It's in the collection.
Yeah, thank you. Thank you.
Yeah.
Thanks for inviting me, y'all.
All right, folks.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.